Atmospheric Science students, Dr. Shragi here. We are ready to start learning how to work with meteorological observations. We're actually going to be able to do some decoding of real observations that really come in over the system called the LDM, but we'll talk more about that in a different lecture. I want to show you before I go to the PowerPoint though what the program is going to do. I've made a program called Assignment 8 because that's the one you're on. If I compile my copy of Assignment 8.c, it works just fine. And I'm going to show you what happens when I run it. It says enter the 4-digit identifier of a station. What this program does is it takes a current observation file that has all the observations coming in all around the world, the current hour, and it's going to tell you, you put in a 4-character station identifier and it's going to tell you what the weather is at that station. So you're going to be making the same program, by the way. So like if I type in KOMA, which is the station identifier for Omaha, you find out that currently in Omaha is 28 degrees Fahrenheit, dew point is 19. Oh my goodness, it's so chilly. Okay, I actually here in my home in Indiana do not have the system set up that I described in a different lecture that brings in the current data. This is just something I had archived, a particular old set of observations that I have saved. I'll even show you what I'm talking about in just a second. But anyway, so obviously this is not really current. I'm recording this in July. Clearly it's not 28 degrees in Omaha. If I run the program again though, I could choose a different one. Here's KLAF, that's Lafayette, Indiana. It's 27 degrees in Lafayette. We could run the program again. And again, we could, KEVV is Evansville. And it's 33 degrees in Evansville. Again, it's like 96 in Evansville right now. Old data. It's an old data file. If I go back over here and just show you, the name of the file is current_SAO_WXP. This happens to be the format of a data file in text. We can even look at that file, current_SAO_WXP, and you can see that it is just this big file that contains weather observations. Lots and lots of weather observations in a code. Depending on what meteorological classes you've had before, you may be familiar with the surface code known as METAR. Okay, these are not quite in METAR, they've actually been partially decoded already. But, like for example, if I just do a search here on KOMA, here's the line then for Omaha. 289 is going to be 28.9 degrees, 190 means the dew point is 19.0 degrees, etc. There's all this information in here that describes the weather in Omaha. You're going to be writing a program where the user enters a station identifier and then you give them the observation that is in the current_SAO_WXP file. If everything was working right, current_SAO_WXP would always have the most recent hour's data. As it happens, it doesn't because it's not all set up right for me here in Indiana, but that's okay. The process is the same. So, but to get to that point, man, what a cool program. To get to that point, though, we got a lot of steps to get through. So I'm going to switch over here to my PowerPoint. And I apologize, this particular PowerPoint did not render all that well for me. I'm not sure, well, you have the original PowerPoint available to you on Blue Line, so you can get it yourself, but for some reason this one didn't render quite so well. So let's learn about these meteorological data. There's a number of different steps. This program requires a couple of different things that are new techniques to us. Something called typecasting, a variable type called strings. We're going to have to learn how to use the if statement in C and how to use the end of file function in C. But we'll get there. They're all just stuff, just new things to learn. Typecasting. Typecasting is a technique that you use in C and other programming languages that changes a variable from one type, like integer or float, to the other, particularly for integers and floats. Remember, integers are a counting number. You have 7 rabbits. There's no such thing as 7.1 rabbits. There's no such thing as 6.9 rabbits. There are 7 rabbits. They are an indivisible integer. Okay? You can't have 7.1 rabbits. But you could have 7.1 pounds of rabbit, right? Measurements tend to be floating point numbers. But there's all kinds of reasons why you might need to switch between one and another. For example, in this little piece of code that I'm providing to you right here in this program here, I made 2 variables called, well, one was a floating point number that I called temp, and one is an integer that, just to make things simple, I called it itemp. Okay, so we have an integer and we have a float. Well, if itemp, if I happen to be setting it equal to, let's just say 47, okay, it is literally the integer 47. Okay, we can convert that. We could say temp, which is declared to be a floating point number, is equal to, and then in parentheses, float, itemp. In parentheses, float like that means cast itemp as that type of variable. So itemp, which is an integer, gets converted to a floating point. See, in terms of the computer's memory itself, or on the hard drive or whatever, integers and floating points are actually stored very differently. It isn't like the number 47, the integer, has anything to do with the number 47.0. They are actually very different in how they're stored. So the computer has to actually cast one to be the other. They have to typecast them from one to the other. So like this line would then be creating a floating point variable called temp that is 47.0, okay? Which is very different from 47, like 47 rabbits. But the computer can't do this. Now we're going to need to be able to do that. See how we're converting a temperature from a floating point number to an integer using this typecast. And it becomes literally 47.0000 again, which is a surprisingly different thing in terms of how the computer thinks about it than the number 47. This is going to be a really useful little thing to us when we're doing this, because the code in the current_SAOWXP file expresses the temperature in tenths of a degree Fahrenheit. So like you get a number like 224 to represent the temperature. And 224 is an integer, and it needs to be converted to to the number 224, and then you divide by 10. So 224 means 22.4. The way you do that is change 224, the integer, into 224.0, the floating point number, and then divide by 10. And you can see how that last line of the code is doing that right there. It is converting this floating point number. It takes this temperature code. Let's say I had temp code as 224, it was an integer. Float typecasts that to 224.0, and then you divide that by 10 to get the temperature. Alright, we'll do some experiments with that in a little while, but another thing you need to know about is a type of variable called a string. A string is a set of characters, like a name, or whatever. It's a set of characters all together. You know, maybe an address, maybe in the name of a city, maybe whatever. It's a word. Okay, I hate to use the word because word is actually something else in C. But think of it as like a word. It's a string. It's a set of characters, and you define them as char, C-H-A-R. So like just like we have what types of variables do we have now? Float, integer, file, and now we have char, C-H-A-R. And when you want to declare a variable as a string, you declare it as a char, and then after the string's name, like in this case I'm making a string called station, there'll be a variable that holds a station's name, like KOMA. In little square, there we go. In little square brackets after the the variable's name, you put a number. And that number needs to be bigger than the biggest, longest string you might be putting in there. For example, all these station identifiers are 4 digits long, so that number after station has to be 5. What you're actually doing there is you are telling the computer how many digits or characters there can be. And when you say 5, it means that there's 4 digits and then there's a special end of string character that will be there. So like if it's 5 digits wide, it can hold KOMA and the end of string character, or KEVV and the end of the string character, or whatever. And there is absolutely no harm in making that number bigger. Okay? Feel free, if you're not sure how big these station identifiers are, it would make no harm whatsoever to call it station 5000, where you could have 4,999 character long station name. Hurts nothing. Oh, it wastes a little bit of memory, but computers have more than enough memory. So certainly at least 5 digits long for these station identifiers. In this particular program, what we're going to be using these strings for is they're going to be containing things like the name of the station. You're going to ask the user, enter the station that you are looking for. They're going to type in KOMA or KLAF or something like that, and you are going to store that in like station wanted, which will be a string with at least 5 characters long. Okay, make it 10 or something just to be on the safe side. Or when you're reading through the current_SAOWXP file, you will be reading an observation. You just read in KBOS, Boston. And then you read in temperature and stuff like that. Then this station might be equal to KBOS, and this temperature might be equal to whatever the temperature is, and so on. Strings can be a little bit tricky. C has kind of goofy ways of thinking about strings. For example, it really looks like this line should work. It looks like if I've declared a string called station that has to be no more than 4 digits long, station equals quotation marks KOMA, seems like it would work. If I was inventing C, I would make that work. But it doesn't. Okay? In some programming languages that would work. That would be just fine in BASIC. That would be just fine in Perl. It does not work in C. So instead what you have to use is you have to use a function called strcpy, or string copy. String copy, station, comma, what you want to go into station, works just fine. So here I made my variable called station, and then I'm saying station is equal to quotation marks KOMA. Station is part of the stdio, I'm sorry, not station, string copy is part of the stdio.h library, and so as long as you've included those at the top of your program, you'll be able to use things like string copy. Alright, to actually do something like print a string, you use the printf function, but of course you need to know the format specifier. Since string is a new type of variable, you know that %d works for integers, %f works for floats. You don't actually ever print file addresses, so we don't have a format specifier for file. For strings, it's %s. So %s will give you a way to, like, for example, printf, %s, and then station. The contents of station will go in where that %s is. And we'll do some examples of this a little bit. In the same way, you can use scanf or fscanf to get a string from either the keyboard using scanf or from a file using fscanf, where you would be reading in %s format a string, and you put it in with ampersand station, just like that. Now, I'm going to tell you right here now, there might be a mistake here. I actually do my research in a couple of different programming languages, and I get this always confused. I can't remember. Maybe there isn't an ampersand there. We'll test that, okay? Oh, in fact, let's test that now before we move on to the next part of the program. Let's go ahead and bust out of this and go, look at my program here. Let's make a new program. We'll call this, how about string test? Just to make a little program here. I'm going to say #include math.h and #include stdio.h. Oops. Alright. Let's just make a fairly simple little thing here. I'm going to make a character string called name. And I'll make it at least, it can't be as much as 20 characters long, let's just say. Printf. Enter your last name. I'm prompting the user for some input. Now, I will scanf from this scanf means from the keyboard, a string, ampersand name. Okay, see, I'm reading in, they're going to enter a name, and it'll be stored in a variable called name that has up to 20 characters in it. And then let's just, oops, I hit the cap lock key there. And then let's printf, that is a nice name, comma, %s, name. Okay, so like it'll ask you for your name, and then it'll say, that's a nice name, comma, and then whatever your name is. Alright, now that's a totally stupid program. The only part of this, I have to admit, again, just because I do things in different languages I can't remember, is whether or not we need this ampersand. We certainly would need this ampersand if this was a float or if it was an integer, but it seems to me there's something goofy about it doesn't need it for string. Let's try it. If I say gcc string test.c -lm, oh, warning, format %s expects an argument of type char star, but argument has type char star 20. Alright, yes, in other words, it does not want the ampersand there. I don't know why that error means that, but if I take the ampersand out, so for some reason for strings you don't need that ampersand there. Let's compile it again. This time we got no errors. Enter that there. Enter your last name, Shragi. That's a nice name there, Shragi. Alright, run it again. Enter your last name, Smith. That's a nice name, Smith. Alright, simple little program just demonstrating what we can do with strings. Real quick here, what if we tried something else? We could reuse that variable. We could say strcpy. We could copy into the word name. How about, I don't know, Johnson. Okay. Printf. Do you know Mr. %s? Okay, so we are using string copy to put the word Johnson into name, and then it's asking, do you know Mr. Johnson? Alright, and let's just see if that works. Got to recompile it. Whoops. Compile. Let me clear that out and show you what I did there. GCC string test.c minus lm. Oh, what am I doing here? String copy name and Johnson. Why doesn't that work? strcpy name Johnson. Why doesn't that work? What am I doing wrong here? Hold on. strcpy start.c. That's the only one. I'll have to figure out what's going on there. Something's going on here. Do I need... I'll have to double check. There may be that there needs to... I'll send it to you as an email or something like that, and if I don't, if you haven't heard, let me know. It could be that there's a different pound include. There could be a pound include string.h that needs to be here. In fact, let's go ahead and just try that. GCC. Compile it. Enter your name, Shruggy. Shruggy, that's a nice name, Shruggy. Do you know Mr. Johnson? Okay, so you do have to have that pound include string.h. It's just another set of libraries that somebody has written in order to use strcpy. You learn something new every day. Did I actually have that in my copy of assignment 8? No, I didn't. I wonder how I did it. Okay, well, we'll find that out. But string.h is apparently something that you need. Who knew? Alright, let's continue. It's very hot in my house. Alright. Another thing that we need. I can't believe we've gotten this far in the semester and haven't used the if statement. I mean, if is such an important thing. It's how you make decisions in a program. If this, then this. Or if this, then this, or else that. Using combination with else, you can create programs that do all kinds of interesting things. And it's actually not terribly complicated to see how it's going to work. I mean, let's say here we have a little piece of program here. This program is going to be scanning in the temperature from the user, okay? We're saying scanf % in floating point format of number with the temperature. If temperature is less than 0, notice how that's in parentheses. If this thing is true, that's in parentheses. Temperature less than 0? If that's true, then do what it says there in curly braces. I don't know why those circles are in the wrong place. Do the stuff that's in the curly brace. Like in this case, it's printing, it is cold. Okay? So in this case, that means just print to the screen, it is cold. If you want something a little bit more complicated, for example, then you could say else and have another set of curly braces and have it do something else. So if temp is less than 0, it'll print it is cold, else it'll print not too bad. Okay? It'll do one or the other. If the condition is false, then if temp is not less than 0, it'll go do the thing that's in that else bracket right there. Okay, I mean, this is not so terribly difficult to think through how this is going to be. In this case, it'll just be printing this, not too bad. There is one sneaky little thing here. In these if statements, it's very easy to say, like, if temp is less than 0, or if temp is greater than 100, or something like that. But what if you mean equals? Like, if I equals j. This is a complicated point. You don't use equals, you use equals equals. Two equal signs next to each other. Two equal signs next to each other means is equal to. Like it's a test. One equal sign is an assignment. I equals j means take the value of j and put it into I. I equals j is a question. Is I equal to j? It's a trick of the English language that we use the word equals to mean a couple of different things that in fact have very little to do with each other. We mean, you know, pi equals 3.159 means take the number 3.14159 and put it into the variable pi. If number of rabbits equals 10, then if number of rabbits equals 12, then print you have a dozen rabbits, is a very different statement. What you really mean is if number of rabbits you have equals 12, okay? It's just a different verb. It means test this, okay? Single equals is for assigning a value, equals is for testing a value. And actually, that's a good, I mean, almost every programming language out there requires that difference there. In general, floats cannot be equal to each other. So don't even try that, but that's rarely a problem. Like, for example, you can't ask somebody, you can't read in the temperature at one station and read in the temperature at another and see if they're equal. Because, I mean, that's kind of a philosophical problem, right? How could two temperatures be equal to each other? Surely if you measured it out to enough digits, they wouldn't be equal to each other. So, Yeah, but this I don't think ever comes up in our class or whatever. In the same way, by the way, you can't use equals equals for strings. It seems like you could say, like you've asked for a station identifier, let's say you put it into your station. That's what they've asked for. You have a string called your station. And let's say I have a station that I just read in from a file, I'll call that string my station. Seems like you should be able to say, if my station equals your station, then print I found your station, or something like that. But that actually doesn't work. You have to use a different function that's built in called strcmp, or string compare, where you just compare string 1 comma string 2. But even weirder, it has to have an exclamation point in front of it. Exclamation point means not. String compare returns false if they're the same, and true if they are different. Well, most of the time what you really want is the other way around, right? You want it to be true if they're the same, and false if they're different. So, bang string compare, or exclamation point string compare, or damn it string compare, whatever little thing you want to use to remember the exclamation point, is the way you do a string compare of two strings. Alright, before we move into feof, let's do a little test of this idea here. Let me go back into my, what was that, string test or something like that? Enter your last name. That is a nice name. Okay, let me just thin this out a little bit. Let's make this a simpler program. Let's just give myself an integer I, and let's just say for I equals 0 to less than 10, I plus plus. We're just going to have a little loop that it runs through 10 times. And let's just say if I is less than 5, something's going to happen. We'll print f. Turns out that %I is less than 5. Oops, I don't know what I'm doing there. Sorry. Hey, come back here. Close this all up. What am I doing wrong here? Sorry, got lost in the menu there. Is less than 5. Alright. See what's going to happen here? We're going to go through a loop 10 times. Each time we're going to test I. If I is less than 5, it's going to write, turns out that this number I is less than 5. Let's just see what that program does. gcc stringtest.c minus lm. Run that bad boy. Turns out that 0 is less than 5, turns out that 1 is less than 5, turns out that 2 is less than 5, turns out that 3 is less than 5, turns out that 4 is less than 5, but that's the end of it then, because all the rest of the times it wasn't. You can test that by saying else printf no percent is not less than 5. Like that. Yep, that looks good to me. Let's compile it. Let's run it. 0 is less than 5, 1, 2, 3, 4 is less than 5. Nope, 5 is not less than 5, 6 is not less than 5, all the way up to 9 is less than 5. Just a simple little example of an if statement. None of that was exactly rocket science. Alright, how about feof? When we're actually reading in that current underscore SAOWXP file, you're not going to in advance know how many lines it has. The particular one I'm giving you is actually an old one, it's not changing. But the real, like if this was actually working, the current underscore SAOWXP file would actually constantly be changing as new observations came in. You don't know in advance how many lines it is. That sounds like a while statement, doesn't it? While we're not done reading the file, read the next observation. So like you would open up your current underscore SAOWXP file, and while you're not done reading that file, read the next line. Sounds good. The command, the function in C that can determine whether or not a file is done, whether you have reached the end of it or not, is feof. Alright, so we have this function that's going to be doing something like, let me walk you through this here a little bit here. So I've opened up, some semesters I actually the working version of current underscore SAOWXP is actually stored in this particular strange directory structure. But we don't need that right now. It's just going to be in your directory. Okay, just put a copy of it in your home directory. Then while something's going to happen right here, read in an observation. And then when you're done reading them all, close your file. The question is, what goes in here? Well, what we mean is, while we're not done reading the file, while we are not at the end of the file, Well, the end of the file, how does a computer know when it's at an end of a file? Well, there's a special byte that means end of file marker. When your computer is hit in the hard drive, it hits the first byte, and then it reads that long string, that long file rather, of all those ones and zeros that make up all those bytes. When it gets to a special one of those 256 possible bytes, that special one is called the end of file marker, and it tells it that you are now done. So we're going to keep reading this current underscore SAOWXP file until we hit the end of file marker. So while we're not at the end of the file, while we are not specifically at the end of the file that we're calling, in this case, fin, the input file, well, that is a function called feof fin. Feof fin is a question. It's going to return either true or false. Are we at the end of the file? Well, I just told you a little while ago that exclamation point means not. So while we are not at the end of the file, then read in an observation. Oh, that's so slick. This is an important trick. Reading in data that we don't know how many lines there are in advance. Just put it inside of a while loop. While loops are great when you don't know in advance, you're just testing. While we're not at the end of the file, read one more line. While we're not at the file, just read in one more line. Now, I was going to, at this point, tell you about how we actually get these observations, but I want to modify that lecture, so I took those slides out. But for now, what I want you to do is to go and get yourself a copy of the current underscore SAOWXP file, which is from the ~ej directory on Chesapeake, and just use that. It's an old version of a file from some time in the past. Actually, I think it's fairly far in the past, like 10 years ago or something. But it works just fine. It has plenty of observations. It'll work good. And it's going to look something like this. The top of the file has a couple of things in there. The first line says WXP SFC. It just tells it that it's in the WXP surface file format. You're going to get past that line using the skip to end of line function that I'll be showing you. Now that second line will always be the time that the observations were taken. This version of the file that I happened to use when I made my PowerPoint was from 2004 of all things. But it's a mixture of characters and so on to make the date string. Just use this code that I'm providing here. Give yourself a variable called timecode that's a string, and then use fscanf to read in. Just take literally these strings. This is a very sneaky thing in C. You're never going to use that again. Just go ahead and it isn't worth learning how to do all that. Just take it and it will put those variables into scan timecode. Again, I'm not 100% certain that ampersand should be there. Then, after that line is decoded, there's thousands of observations. All right, we don't know in advance how many there's going to be. And each observation consists of these values. So what you're going to do is, while you're not at the end of the file, read in a string. That's the station identifier. There's lots of them because it's all around the world. Declare it to be at least 5 characters long. And then that second number will be the integer code that corresponds to a temperature in tenths of a degree. So I would call that something like temp code, and then use typecasting to change that into an actual temperature in Fahrenheit. The third value is an integer that codes up in the same sort of way for dew point. Pretty straightforward. Again, the textbook makes this more clear, I think. The fourth value is the integer that codes up the wind speed and the direction. For now, just read that. Okay? I'll be able to help you in a little while. That is, getting that code, those 4 digits out into a wind speed and a wind direction is a little trickier. I'll be giving you that kind of information. The fifth value is the altimeter setting. If you don't know what altimeter setting it is a little bit different than sea level pressure. It's a little bit, for now, let's not worry about that. Read that number, call it altimeter setting or something, but don't decode it or don't worry about it. We're not going to use it for anything. And the sixth value is an integer that codes up to mean the sea level pressure. I'm going to give you a function that can decode this, but we'll get there. Okay? For now, just read in pressure. Okay? Read the number, this integer here that codes up to be the pressure, but don't worry about decoding it right now. The rest of the line contains all kinds of comments and the visibility codes and all kinds of stuff that I don't really care about for the purposes of this class. We can skip to the end of this line using the skip to end of line function that I'm going to be giving you. Skip to end of line is a really powerful little tool that really ought to be built into standard input and output, but it isn't. But you can then skip to the end of the line so you're ready to start reading the next observation. So what you're going to be doing is you prompt the user to enter a station identifier, and then you read through the current underscore SAOWXP file looking for a station that matches that. When you find 2 stations that have when you find a station whose name matches the one that the user entered, decode that station. Otherwise, just skip to end of line. Neat? This is a pretty smart, slick little program here, and specifically, there's things that I ask for at the end of the chapter here for you to output. Do not try to do everything at once. Do not sit down, try to write this whole program, which might be like 200 lines or something like that, and try to do this all at once. Also, do not wait until the last possible minute to do this assignment. This is the biggest assignment so far by far. It says here to make a copy of current essay on WSP. Don't worry about that. That was what I was thinking, that I was going to be able to get this all working before I recorded lectures, and I have not gotten it working. Alright, well this is going to be a fun little assignment, because once it's done, you've really got a powerful tool here. This ability to just, type in here, a station identifier, A dot out, whatever, KVOS. I see, that's the problem, I didn't have this. GCC assignment 8.c, A dot out, put in a station identifier like KBOS, and you get to find out what the weather is there. And again, if I had this working where it was actually the current observations, that would even be cooler. But as it is, it's still the basic idea, the same techniques. Alright, I think that's everything that you need to do this assignment. I'm excited for you. This is an interesting challenge. I envy you getting to do it for the first time. Alright, please let me know if you have any questions. This is Dr. Don Schraube.